sure that all important topics and concepts are sufficiently described. The lecture, as I said, I have more than well, you can already see them in the website as well, right? It's more than 200 slides, but the last part about programming real processing in memory architectures is something that we may cover tomorrow, or finish at least tomorrow. It all depends on how fast we go on the first part, which is what we can call the processing near memory lecture. Okay, so it seems that we are live streaming now. Got it? Okay. And yeah, over the lecture, we will see when to make a break. Maybe we'll finish 5 minutes earlier. We'll see. Yeah, I guess we can start. Any questions? Not for a start? Okay, so then let's go ahead with lecture 3 in this course on computer architecture. Today, as promised, we start the really fascinating part of the course, that is processing in memory. And processing in memory, as we are going to see in a few slides, is divided into different types. Today, we are going to talk about the main first part of processing in memory, which is processing near memory. Remember that processing in memory consists of placing some sort of compute capability in the memory or in the storage. When we talk about processing near memory, what we mean is that we are placing processing elements or compute units or processing cores near the memory arrays or near the storage. So yeah, we already covered, okay, let me also clarify. Tomorrow we will have in principle 2 lectures. In lecture 4A, we will talk about programming a real world processing in memory architecture, because that's what you're gonna do in one of the labs. So you need this background. We are not going to go into a lot of detail, probably because we will also premiere the lecture from last year, which was, pretty long. It was an entire lecture about how to program the admin pin system. And yeah, I will also share some pointers to a lot of material that that will be useful for you to learn how to program this system. The second part of tomorrow's lecture, 4B, it's going to be, like kind of potpourri of different things that need to be done, different challenges that we need to tackle in order to make processing in memory something real, something that can be used in the real world and jumps from the academic or industry research environment where just simulators and prototypes are developed to some real world products that can be and available to all consumers, or potentially all consumers, but it still needs to be done a lot until we can do the seamless, let's say, end-to-end integration, system integration. Okay, and then next week, at least the first lecture will be also about processing in memory. It will be the other, a big part of processing in memory, which is what we call processing using memory. In next week's lecture, you will have Geraldo Francisco de Oliveira teaching. He is one of our PhD students, and he is a real expert on the topic, because that's what he's doing in his PhD. So for sure, I think he will give a very good lecture. Okay, so let's start with this lecture 3, processing near memory. And first of all, we need to recap a little bit on things that we covered already last year. What's the motivation for processing in memory? What's what we call processing in memory, and why processing in memory now? Remember that last week we were discussing some major trends affecting main memory. We were also talking about the need for intelligent memory controllers, and we discussed these 3 key systems trends. The first one, that data access is a major bottleneck for the reason that applications are increasingly data hungry. The energy consumption is a key limiter in the systems, and data movement energy dominates compute. We saw some interesting plots last week in order to motivate all of these, and we are going to recap on all of these. But all these challenges allow us to make some observations and also take advantage of some opportunities. There is a high latency and high energy that is caused by data movement due to several reasons. For example, that we have long and energy-hungry interconnects. These interconnects are based on electrical interfaces, so they are also very much energy-hungry, and we are moving large amounts of data. The reason is that data is increasing continuously. We are handling more and more or bigger and bigger data sets these days. But this represents an opportunity, which is the possibility of minimizing data movement by performing computation directly inside the memory or close to the memory. And that's what we call processing in memory or near, in-memory computation or in-memory processing or near data processing. It's a even more general term that encompasses also storage, right? So like something like the cache, the SSDs, the main memory, even the network or the memory controllers, if we equip these devices or these parts of the system with some compute capability, we can talk about near data processing, right? In this course, we mostly talk about processing in memory, but that's probably because, you know, initially the focus was on equipping the main memory with such compute capabilities, and that's why we are kind of inheriting the term processing in memory and making it, you know, wider and encompassing all these possible memory spaces that we focus on. This is one of the key directions in this course and also in our research. Remember this slide from the first day. One of the key issues and one of the topics is fundamentally energy efficient architectures, memory-centric and data-centric architecture. So in these lectures, we are talking about processing in memory. We are talking about how to build memory-centric or data-centric architectures. Yeah, this is a motivating slide from Professor Mutlu about Maslow's hierarchy of needs. You know, like all the different needs depending on what's the status of the accomplishment, right? If we translate these to the computing systems, probably what we want at the very bottom as the basic needs are everlasting energy. And why is that? Because we want a sustainable world, right? We want a world that looks like this and not like this. And that requires us to be very much energy efficient, right? Energy efficient and also high performance and also sustainable all at the same time. And this is something that we can achieve by making compute systems more data-centric or more memory-centric. And we are going to see in this course how. The problem that we want to solve with these kind of systems is data access, data movement, because our current design principles cause a great energy waste and also a great performance loss. We have already seen some motivating examples. We are going to review them today, and we will go into the possible solution that is processing in memory, because processing so far is done very far away from the data. And what's the reason for that? The reason for that is how the systems are built from the top to the bottom. If you think about the von Neumann bottleneck, about the von Neumann model, sometimes we talk about the von Neumann bottleneck when we mean memory bottleneck or data movement bottlenecks. That's why I said that. But I wanted to talk about the von Neumann model, which is supposedly the cost of that bottleneck. There are three key components: computation, communication, and storage and memory. And they look like this, right? We have the compute unit here, we have the memory and storage units on the other side, and in between we have a channel, a communication unit, to bring data from the memory and the storage to the compute units, and once we are done with computation, return the results there, right? Typically, this memory storage unit is divided into the memory subsystem and the storage subsystem, right? And this is how these systems looks, right? Supposedly, the problem is, well, not supposedly, the real problem is that this design is overwhelmingly processor-centric, right? Why is that? Because all computation is done here, while the memory and the storage are dumb. They are not optimized at all to perform anything different from just keeping bits, right? Storing bits. And that's where the problem appears, because the way that these different units have evolved over time has been at different rates. If you think about, well, I think I already mentioned these numbers last year as motivation, but if you think about how much compute units have improved in the last decade or in the last 30 years, you will see that they have done much more and much faster than the memory and the storage, according to different metrics like energy consumption or performance, or and regarding the memory bandwidth, latency, etc. We already discussed all of these. And in between, the communication unit is also, pretty narrow. It's like a funnel, right? We don't have like a very wide highway where we can transport a lot of data at the same time. In the end, this is sort of a funnel. So every time we need to go here, we'll have to, enqueue requests and go one by one, bring the data from the memory and the storage to the compute units. And that's what makes the system, that's what creates this memory or this data movement bottleneck. As I said earlier, sometimes it's also called the von Neumann bottleneck, because the key reason for the bottleneck is in the way that the system is built from the beginning. And that's something that is already known for many years. Remember this interview with Richard Seitz already in the 90s. I think that this is probably the most important excerpt of this interview with respect to the current lecture, is that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. And he was thinking about the coming decade, probably 2 decades later, still the problem is the same. And let's very quickly review some of the motivation results that I showed you last week. First of all, this nice plot from Professor Mutlu's PhD thesis, where we can see that more than 55% of the execution time is spent on bringing data from the main memory to the cache hierarchy. Remember that this is the paper, this is a shorter version of the paper, and I also pointed you to this interview. But more recently, we can check more recent studies, for example, this one from Google in 2015, where they use the top-down approach, the top-down methodology to characterize the workloads and see where the pipeline slots, the pipeline cycles are being spent. Remember that in the ideal world, we will have 100% retiring, meaning that we are making full use of the pipeline, right? And we are productive all the time, but unfortunately, that's not the case. And we see that in most of the workloads, most of the time is spent on the backend, and the backend means the compute units, but most of these cycles are spent on accessing the memory units. And with a little bit more detail in this figure as well, we can see that half of the cycles are spent stalled on cache, so waiting for data coming from the main memory. And this happens because current processor-centric designs are grossly imbalanced in the sense that processing is only done in one place. Data needs to move all the time from the memory and the storage to the processing elements, and then the results going back to the memory and the storage. And this is energy inefficient, is low performance, and is complex. And trying to mitigate these issues with processor-centric designs, processors have become more and more complex over time. And that in reality doesn't really help, even though it was all designed to tolerate the data access in some way. But that made us create very complex hierarchies. Remember that CPUs, for example, these days have 3 levels of caches, and also complex mechanisms like prefetching. And people keep working on that, improving these techniques that are effective until to some extent, but they unfortunately didn't solve all the problems. The system still is very energy inefficient, low performance, and complex. Remember also this picture from last week, even though most of the compute system is devoted to memory, but still we have these perils of processor-centric designs. In terms of energy, we already saw this slide comparing the total energy to perform a complex arithmetic operation to the energy spent on accessing DRAM for reading or writing, and we see that there are 2 or 3 orders of magnitude difference. Or we also saw this graph the other day comparing the energy for a 32-bit operation from an integer addition to an access to DRAM, and we can see a huge difference of more than 6,000 times more energy on in a memory access than a simple integer addition. Or for even more motivation, you have another slide here. This one shows 41% of mobile system energy during web browsing is spent on moving data. This is a study from 2014, or more than 100 times is the energy of a memory access with respect to an add operation, in line with the results that we have seen in the previous slides. And also, you must remember this slide. We are going to discuss this paper, by the way, today. We are going to discuss this work. But yeah, this is a kind of a very highlight number. 62.7% of total system energy is spent on data movement. The main reason is that bringing data to the processor is much more expensive than computing on that data. Okay, so we can fix this situation, right? We can make compute systems more memory-centric. We can, overcome all these perils of processor-centric designs, but this requires us to think in a different way and try different approaches. In the end, we need a paradigm shift, right? Where we enable computation with minimal data movement, and we compute where it makes sense. Where it makes sense means where the data is, right? Let's try not to move data. Let's try to just send the computation to wherever the data is. And that might be in the processor itself, might be in the caches, or might be in memory or in storage. The goal is to make computing architectures more data-centric. So now, instead of thinking about memory as just a dumb space that stores zeros and ones, we can think about it like something else, like an accelerator, where we kind of load computation from the main system. For example, this could be like a system on a chip, right? With CPU cores, GPU cores, and also some video or imaging accelerators. So we could send some computation. We will see what type of computation. Of course, this memory is not going to be ideal for any sort of computation, but for some particular operations, it will be very good. It will be much faster than the CPU or the GPU. So now we should see the memory as an accelerator, more similar to a conventional accelerator. But don't forget that is an accelerator. We will still have a host processor, which is the CPU or the GPU, or both of them, that can access stored data in memory and also send some computation to the memory to be performed there. For example, we could have some workload running here, like a database, and perform queries directly in memory, assuming that we have some processing elements inside the memory or near the memory. We can offload a query to the memory, and the memory will return the results when they are ready, right? This sounds like a very good idea, but of course is something that is not so easy or so direct to enable, right? There are other design considerations that we have to think about and need to find solutions for the respective challenges. For example, if we make the memory compute capable, what should we do with the controller? Should we also make the controller compute capable, or how should the processor communicate through the memory controller to the memory units? Or so how do we need to design the processor chip itself? Do we need to change something in the cache hierarchy, for example? And how do we have to design the in-memory processing elements or in-memory units? And how do we program these systems? We need a new hardware-software interface, probably. We need a new ISA, and we also need new high-level ways or high-level frameworks to program this new system, and that might require us to develop new system software, new compilers, or even new programming languages, right? And we will also have to rethink algorithms as well. And I think I mentioned already last week some examples of algorithm, hardware co-design. I think that we are going to go over them again today, right? So many things need to change in the system in order to enable and adopt processing in memory, and all of that requires changes, you know, in the entire transformation hierarchy. We are going to talk about these different challenges and the potential solutions in detail tomorrow in lecture 4B about enabling processing in memory, but I wanted to mention it well in advance in order for you to understand why over the remaining part of this lecture, where we are going to discuss real world systems, and also we are going to discuss some, you know, academic proposals for processing in memory, but you will understand as well why we pay attention to certain aspects of the system integration. For example, how to deal with cache coherence, or how to deal with virtual memory address translation, for example. Okay, as an introduction to processing in memory, remember that this is a highly recommended reading. I don't know if it will be required or not. That's something to decide yet, I believe, but for sure is a very good reference. I think that most of the things that I'm going to explain today and tomorrow, and also what Geraldo will explain next week, is already in this book chapter. It's pretty long, but it's also very comprehensive, and I think very useful reading for all of you. This is the abstract, and here you can see the table of contents. We start in a very similar way as these lectures and this course, right? Motivating why processing in memory is needed, discussing what are the main trends affecting main memory. Then we introduce processing in memory, the two main approaches: processing using memory, processing near memory, and finally the enabling adoption part. All of this is about processing data where it makes sense. And it's a paradigm shift that we need to do in order to make compute systems more data-centric, but it's not just a new idea that we started here today or 2 years ago. No, it's an idea that has been explored for 50 years. The first paper that we are aware of is this one from William Kautz in the IEEE Transactions on Computers in 1969 with the title Cellular Logic in Memory Arrays, idea of extending memory arrays with some sort of compute capability near each of the memory cells. Or 1 year later, we can find this other one, A Logic in Memory Computer by Harold Stone. So processing in memory is an old idea, but it was really difficult to make it real. Why was that? Because there were many challenges to solve. Remember that there are many things we still need to do in order to, you know, make processing in memory universal or ubiquitous, right? Or at least available to the compute systems that can really benefit from processing in memory. I'm not going to discuss what have been those, say, historical challenges, but they are mostly related to the, you know, how advanced technology was, right? If you think about the way that a processor is designed and is fabricated in CMOS logic, or how DRAM is designed and fabricated with DRAM technology, if you compare these two, you will see that because the requirements of each type of device are different, also the way that the technology has evolved is different. And now, if you want to integrate a processor or an ALU inside the memory using DRAM technology, that's, you know, it's pretty challenging to design. Those are the, you know, key reasons. Of course, there are ways of overcoming these challenges over time, but you see, it took us like 50 years, right? Okay, but now is the right time for in-memory computation because there are huge problems with the memory technology. Remember that there are problems related to how memory scaling, DRAM scaling is an example. Undesired phenomenons like RowHammer, for example, that can represent a real security issue. There is also a huge demand for applications. We are running more and more applications and more varied applications in our compute systems, and accessing data is always an issue, right? And that entails energy and power bottlenecks and performance bottlenecks as well. And the designs are somehow squeezed in the middle. So now it's it's the right time to try to overcome all these different issues with in-memory computation. We can say that the recent developments in processing in-memory systems, even though processing in memory was proposed 50 years ago, but more recent developments started maybe in the last decade when this hybrid memory cube consortium appeared. It was led by Micron, one of the major DRAM vendors, and it's a 3D stack memory, or it was a 3D stack memory, several layers of DRAM, and at the bottom a CMOS layer that was called the logic layer, as you can see here. And in this logic layer, you have certain logic that is necessary to access memory. You have, again, small memory controllers there to access the different memory banks in the different layers. By the way, if you look at this from the top, you will see that the logic layer, well, not only the logic layer, but also the DRAM layers on top are divided into different parts, and each of them is called a vault. And at the bottom of each vault there was a memory controller to access the data in that vault. But the logic layer had also some spare area, right? Some area, some part of some silicon that was unused. So it was possible at least to think about potentially embedding some compute capability in that logic layer. And that's what inspired many people in industry and in academia to do research in this direction. What would happen if we have access to this 3D stack memory with a logic layer where we can place a small CPU core or a small accelerator for certain operations that we want to accelerate, okay? So this is like, as I said, this was very inspiring for a lot of research, and that's why we are going to review some of those interesting proposals, but there have been more attempts from industry, more recent attempts from industry as well. For example, from Micron, something different called the automata processing, or the UpMem PIM architecture that you are going to work with, and we will start covering with more detail today. Also the prototypes from Samsung, from SK Hynix. We are going to see a couple of slides about these ones as well. The other one from Samsung that is called AXDIM, or this other one from Alibaba for recommendation systems. As I said, we are going to talk about them. Okay. And there are many other experimental chips and startups that are not in this slide, but as soon as you type in Google and search, you will find different ones as well, or a few more as well. Unmuted. Is there any question? No? Okay. Do you guys have any questions so far? Okay, yeah, so let's, well, we are discussing why in-memory computation today, and in-memory computation requires system integration. We will also need intelligent memory controllers to communicate with the processing in-memory units, right? So that's why this slide is again here. Remember that, if you want to review all the different issues regarding memory scaling, this is a paper that you can check. A few of them are also discussed in this work. We are going to cover this work today. Yeah, because this one motivates on why processing in memory is needed, and why applications, for example, have issues when scaling, and how we can propose solutions for those applications. Okay, yeah, let's go quickly over these few slides about the real-world processing in memory systems before we go into details on the different approaches that we can make to processing near memory. Okay, no questions? Okay, so the UpMem PIM architecture, you have already seen this slide last week. It's based on DDR4 memory technology inside each of the chips, you find not only memory, but also small processors that are called DPUs. They are pretty slow, as you can see, but you have a bunch of them, more than 2,500, and that means that you can accelerate the applications a lot, because you can, or all these 2,560 cores can enjoy a lot of bandwidth from memory, actually more than 2 terabytes in the most updated system. This is how the systems look with the dual socket CPU. There is still some main memory, DRAM, conventional DRAM chips or DRAM DIMMs, and PIM enabled memory. We are going to talk in detail later today and also in tomorrow's lecture, because we have done a lot of work on this architecture, on this processing in memory system, and also because you need to have some background on how to, how the system is built and how to program this system for one of your labs, as I said. Okay, this is also the announcement from Samsung in 2021. They announced a processing in memory system for artificial intelligence and machine learning. Remember that this is based on a 3-stack memory, not HMC, but HBM2, where some of the layers have been modified to integrate processing elements called PCUs or PCU blocks. There is one of these PCU blocks in between 2 banks. And these are relatively simple units, because the system or the processing in memory, this processing in memory architecture is targeted at a specific type of applications that are neural networks, artificial intelligence, machine learning, and these workloads typically mostly need multiply and accumulate operations. And that's why they are so specialized. You have already seen this photo already, where you can see how the DRAM layer has been modified to place this PCU block in between 2 DRAM banks. And this is another picture of the system with the PIM unit between 2 banks. And then if we take a closer look, we'll see that the PIM unit is sitting near the column decoder, write drivers, and sense amplifiers. So that when we open one row, that will be here in the sense amplifiers, this PCU, now it's called SIMD because it's a SIMD unit, has direct access through its own registers. So this is how one of these memory banks would look like. And the PCUs themselves are SIMD units. In total, they have 16 lanes, right? And each of the lanes can operate on 16-bit floating point values. Why is that? Because that data type is pretty useful in machine learning and artificial intelligence. There are, as you may know, and actually I think we are going to mention that later as well, there are different ways of applying quantization to the neural networks in order to reduce the size of the parameters. You could start training a network with 32-bit floating point, but eventually want to reduce that in order to save storage and to compute faster, right? Because networks are robust, so they can still produce accurate results, even though we may want to reduce the precision by doing quantization. 16-bit floating point is kind of a standard thing, and that's why they focus on this. And also observe that this is a SIMD unit. SIMD meaning single instruction, multiple data, meaning we have 16 of these lanes, each of them operating on different data, but all of them performing the same operation. For example, a multiplication, for example, an addition, or a multiply accumulate operation. And why does it make sense that this is SIMD computation? Because the type of workloads that we are targeting here require a lot or have a lot of data parallelism. For example, matrix multiplication or matrix vector multiplication are widely used in machine learning and neural networks. So makes sense to have multiple of these lanes computing in parallel, because we can operate on multiple rows and columns at the same time. So this is an important, let's say, smart way of exploiting the, not only smart, but also conventional way of exploiting the data level parallelism. Something pretty interesting as well of this Samsung PIM architecture is that it can be, more easily integrated into a real system because it's compliant with a modified JEDEC controllers. JEDEC is the standardization institution that creates the standards for the different types of memories, different types of DRAM, right? And they define how the host system has to operate the memory. What are the latencies that need to be respected? How frequently needs to be refreshed? The DRAM rows, etc. If you want to integrate a new type of memory like this HBM PIM or Samsung, it's called HBM PIM or FIM DRAM. As this prototype from Samsung, if you want to integrate it into a real system with a CPU or with a GPU, you may need to modify the memory controller for the system to communicate with the PIM units, right? But it's not that easy to change the standards and change the way that JEDEC controllers already work, right? Because observe as well or think as well that they are fabricated typically by different people, by different companies. If you think about what are the companies that manufacture CPUs or GPUs, these are different from the companies that manufacture DRAM. For an easier integration, Samsung devised this HBM PIN system as JEDEC compliant. We are not going to go into the details about how the communication is done between the host system and the PIM units, but I'm going to refer you to a longer lecture that covers this architecture with a lot of detail if you want to learn about that, how that can be done. If we take a closer look at the PCU or the PIM unit, you'll see that it has, an execution unit with a pipeline, relatively simple pipeline, but yeah, it has an array of multipliers and an array of others as well. There are also some registers. This sequencer is to access this CRF that contains the instructions themselves. Remember that here we are performing kind of simple computation, mostly focusing on dot product operation or GenV or matrix multiplication. So we don't really need many instructions to perform those operations. That's why there are only 32 different instructions that you can hold there. And the way to program this is using this instruction set with addition, multiplication, multiply, accumulate, multiply, add, and then a few more instructions for data movement, jump, etc. As I said, we have longer lectures about this real-world PIM architecture, and here you have a link if you are interested and want to take a look. Another real prototype, also from Samsung, is completely different. Instead of using HBM2 memory, this is a DIMM-based solution with this AXDIMM buffer that supposedly contains an FPGA, and you can program this FPGA for the specific operations that you want to perform. For example, in their first work, they presented an accelerator for the sparse embedding operators that are used in recommendation systems. If you look at how the typical recommendation system is works internally, it has some parts of the computation that are more dense. They are more they have more data level parallelism, typically multi-layer perceptron networks that are pretty dense, and you can solve them efficiently, usually in CPUs or GPUs, because you can use optimization techniques like tiling and bring large chunks of data to the large tiles of data to the cache hierarchy and their compute. So that's pretty efficient, but other parts require more irregular, more sparse memory accesses. So those are not good for the main processor, for the CPU or the GPU. So those are very good candidates for processing in memory. And that's why in this first paper, what they propose is an accelerator for this operation that in reality is pretty simple. It's sort of a reduction operation or even vector addition operation, something like that. That's why it's, if you look at this NMP unit, NMP meaning near memory processing unit is pretty simple with just an array of others to bring data from the memory ranks to the this array of others, perform some additions there, and store results in this buffer of partial sum. But this is like a all design to get integrated into the FPGA. What's the key advantage of this approach? The key advantage is that we are exploiting rank level parallelism. Typically, in one DRAM DIMM, you have more than one rank. You typically have 2 ranks, but you can only access one of them at a time, right? If you place these near memory processing units near the ranks, this means that they can operate independently and you can access both ranks at the same time, in this way exploiting more parallelism. And this is another figure about how the interaction with the CPU would be done, because everything is controlled from the overall execution is controlled by the host processor, right? And is this host processor the one that needs to offload the computation to the near memory processing units? So the first thing that the processor would do is to write the embedding tables, those tables that are going to be placed here in the memory ranks and need to be accessed, with the regular access patterns, as I said. And when the tables are written there, the CPU can change the mode and go to the processing in memory mode, essentially launch the execution of the SLS operator, which is the operation that runs on the near memory processing units, and then the near memory processing units start the execution. In the meantime, what the CPU is doing is checking a specific status register that will indicate when the computation is done. All these registers are memory mapped, so they can be accessed by the host processor as if they were regular memory addresses in memory, okay? Yeah, again, if you want to learn more about this, here you have a full lecture of 32 minutes in duration. Another interesting prototype also under development right now from SK Hynix is SK Hynix AIM, or accelerator in memory. Similar in spirit to the HBM PIM or FIMDRAM from Samsung, because it's targeting the same type of workloads, machine learning and artificial intelligence, and also is a similar approach. But here, instead of having one processing unit every 2 banks, we have one processing unit every bank. And the memory technology is not HBM2, is GDDR6. But if you look at the internals of this PU, you'll see that what it has is multiply and accumulate units. It also has some units for activation functions. Is something pretty interesting from this architecture. Here is where you can see the PU. You see an array of multipliers, and then it has another 3. Why do we need that? Because if you think about a dot product operation, row times column, what you need to do is, first of all, perform multiplication, and then you need to accumulate, right, in order to obtain a single scalar per dot product operation, right? And that's what we obtain from here. After that, it's possible to execute an activation function that, as you may know, is key for many machine learning algorithms and neural network layers, right? Like softmax or sigmoid or ReLU or GeLU, etc. Right? You have heard of them. What else? Oh, okay. Another something also interesting from this proposal from this SK Hynix AIM is this supplementary SRAM buffer. Inside the DRAM chip, you have these 2 spaces working as a single buffer of size 2 kilobyte that can be used, for example, to move data from one bank to another bank, again, and temporary storage for data movement, or also to store vectors. Basically, think about a neural network, a convolutional neural network. For example, the input is one image, right? And the image, if you are running the neural network inference in these PUs, the image must be coming from the host processor, right? So you could write that image into this global buffer, or at least part of it, and then perform the neural network inference using these processing units. That's the overall idea. Again, if you want to learn more, 35 minutes of lecture about this accelerator in memory. And the last one that I'm going to show you before we go into the, the actual contents of this lecture is this HBM PNM from Alibaba. It's pretty nice from the technology point of view, because it's a 3D stack architecture with one DRAM die and one logic die that are bounded using a technique called hybrid bonding that allows a lot of connections between the DRAM die and the logic die, and this way we can have a lot of bandwidth, very large bandwidth between the DRAM die and the logic die. What do we have in the DRAM die? Well, if you look at this, it more or less looks like a regular memory with some I/O sense amplifiers and some decoder and control logic, right? And at the bottom, we have, of course, the necessary logic to access DRAM, the memory controllers, but also some so-called engines for the specific operations that Alibaba wanted to target here. One of them is called neural engine, the other one is called match engine, and they are designed for different parts of the recommendation system. You see, for example, this coarse grain matching would run on this match engine, while this fine grain ranking runs on this neural engine. By the way, if you look at the neural engine, what you see here is, well, it's mostly a gem unit. Remember the last week we were talking about Google TPUs and systolic arrays. This gem unit is kind of a systolic array, because in that neural engine, what is going to run is a small neural network, okay? But those are different. That's why we need two different types of engines, because the requirements of this two steps of the recommendation system are different. What this part of the picture represents is that these three stages are typically done on GPU because they are very data parallel, but these two are typically, or were typically, performed on the CPU because they have less parallelism and they have more irregular accesses, and that's why they decide, or Alibaba's proposal is to replace the execution on the CPU with an execution on the processing near memory architecture that they are proposing. Again, if you want to learn more, you can take a look at this lecture from our processing in memory course. So these are, I wanted to have these slides here for kind of a motivation about, existing real world processing in memory systems. But as you know, we are organizing as well a tutorial on real world processing in memory systems. So this is going to happen on October 29th. You can attend because it's going to be, everything is going to be live streamed, and we will talk in more detail about these architectures, hopefully, or we will have different talks that might be even more interesting, who knows. But yeah, but there are other real ways of doing processing near memory or near memory processing. For example, this FPGA-based near memory acceleration that we already talked about last week. Okay, so we need to think differently from past approaches, and we are going to see how. This is something that I have already mentioned. There are two main approaches or two main directions to processing in memory. We covered them in the book chapter. We have processing using memory and processing near memory. Today, we focus on this part here. Processing using memory is the topic for lecture 5. This is one first approach to the different types of processing in memory that we can have. Observe that if you read each of these, you will see that we are putting all together under the processing near memory umbrella, but there are certainly important differences between them. It's not the same using logic layers in 3D stack memory than logic in the memory controller or logic near the caches, right? So there are different challenges that you will need to face depending on what's the type of processing near memory, but that would be like the first approach to this classification of processing in memory. There is no, let's say, widely accepted processing in memory taxonomy, but if you look at different taxonomies that people may have proposed, in the end, they all focus on different things or different characteristics that you can use to make the classification. The first one would be the nature of computation, the type of computation. In processing near memory, we are really placing compute elements near the memory, like a small CPU core or a small GPU core or an accelerator or something similar in the end, and ALU that was never there, but now is placed there near the memory arrays. Or we can talk about processing using memory when we take advantage of the analog operational properties of the memory structures. So the classification can also be about the memory technology, but we are mostly focusing on DRAM in this course, but there are also proposals about SRAM or flash memory, etc. And we are going to mention some of them as well in these lectures, and also where exactly the processing in-memory capabilities are. Is it in the sensor, or is it in the storage, or is it in the hard drive, or the SSD, or the main memory, or the cache, or the network, or the interconnect, etc. Okay, so if you take one of these, let's say near memory, DRAM, and main memory, then we have a different type of processing in memory. But still, you could classify even further, because one thing that is not here is the type of computation that you're doing. Is it more general purpose? Is it more application specific? It depends, right? So in the end, the classification is pretty complex. Anyway, best thing that we can do is to start discussing some of the approaches to, or some of the processing near memory proposals, and I think that we will see all of this much more clear. Remember that a lot of the inspiration for the recent academic and industry research on processing in memory came from the hybrid memory cube, a 3-stack memory technology with multiple layers of DRAM, and a logic layer where we have memory controllers, but also can have some processing elements there. It's just one type of processing, is one type of 3D stack memory. There are other 3D stack memories, for example, HBM. As you can see here, HBM has been over the years more successful than HMC, but you know, from the research perspective, they are really very similar. Okay, so if we have one of these 3D memory technologies where we have the possibility of placing compute units near the memory, what's the approach that we are going to follow? How are we going to do it? Well, one possibility could be creating an accelerator, sort of a coarse-grained accelerator based on 3D stack memory, and that could be kind of, you know, equivalent thing to a GPU, right? If you think about your system, you have your CPU there, there's a PCI Express bus, and you have a GPU, a large GPU on the other side, probably discrete GPU for gaming or something else. So that is what we can call a coarse-grained accelerator. Why is it coarse-grained? Because the amount of computation that we offload to the accelerator is relatively large, right? We launch an entire kernel that runs for a few milliseconds at least. So that would be one approach to processing in memory as well. We can create an accelerator of 3D stack cubes that contain a lot of memory, but also contain execution units near the memory. That somehow requires to change the entire system, right? Because now you would be integrating a large accelerator in your system, or maybe we can do something different. Instead of loading a lot of computation to that accelerator, what we can have is some, let's say, simpler units inside the memory and just perform simple function of loading in a similar way as you would do with some of the execution units that a regular CPU or GPU have. If you think a regular CPU, they have SIMD extensions, no, like AVX, and you can write say a short program or a short function that makes use of these SIMD extensions, and you offload the computation there. So in a similar way, you could also do with some execution units near the memory. So it's another potential approach, or even simpler. what would be the minimal processing in memory support, minimal changes to the system and programming. That's also a different proposal that we are going to cover as well. So as you see, we have started this part of the lecture talking about the PIM taxonomy. We can have processing near memory, processing using memory. It might be the type of processing in memory might be with different memory technologies or in different places of the system, the cache, the main memory, the storage. But that's not or let's say those are not the only features that we make use of to perform a classification. If we decide to focus on 3D stack memory and we decide to focus on DRAM and on main memory, still we will have to think about how the processing elements themselves need to be. Do we want these processing elements to execute, a large amount of computation, like a big kernel, and consider them a coarse-grained accelerator, or are we going to offload just simple functions, just maybe, I don't know, 20, 100 instructions, something like that, a relatively simple function of loading, or maybe even finer grain, maybe just a single operation, as if we were using one floating point unit in our compute system, right? Or just a different type of ALU in some sense. So we are going to discuss these different approaches. The first one, we start from the bigger one to the smaller one, and the bigger one is the coarse-grained accelerator, where we need to change more things in the system. The motivation for this coarse-grained processing in memory accelerator is graph processing. Why is that? Well, the first reason for that is that graphs are large and they are becoming even larger. Observe that this is from, well, these numbers here are from 2015, almost, well, 8 years later, right? If you think about the graphs for Wikipedia or Facebook or Twitter or X, which is called now, or Instagram, they could be much bigger, right? Because the number of users has increased, the number of connections has increased as well. So these graphs are larger and larger, right? So that's the first motivation. We need a lot of memory, and we will need a lot of data movement to process these graphs, right? And the second reason is that scaling is very challenging. That's why, well, we have already mentioned this, application scaling. If you take more relevant graph processing algorithms and execute them on a multi-core system and try to increase the number of cores or increase the number of threads according to the number of cores that you have in the system, and perform the computation, you will see that the performance saturates at some point. And the reason is that even though you continue increasing the number of cores, the total bandwidth that is available to these cores is limited. It's very limited because, remember, we need to access data through a thin, a narrow funnel, which is the memory channel, right? Or the memory unit in the von Neumann model. So yeah, these are real example results for 32 cores and certain graph processing algorithm. You can obtain some performance. If you increase the number of cores 4 times, you only get 42% more performance. And that's why, because we are saturating the bandwidth. So it's not as simple as using more cores in the system. Is we require different solutions, more smarter solutions in the end. But yeah, let's discuss why this happens. What are the key bottlenecks in graph processing? The first reason is that the graphs are very large, and the second reason is that the graph algorithms are typically iterative, and that means that we require many iterations to process the entire graph entirely, the graph entirely, right? And also one additional or two more additional bottlenecks are coming from the fact that accesses are typically random because graphs are very sparse. And if you think about each of the nodes in a graph, for example, representing a user of a social network, this user is connected to many other users, but the neighboring user might be connected to completely different other users, right? So two of you might be sitting next to each other, but your friends might be in completely different parts of the world in the end. And that's what makes that when it comes to processing the graph and going over all the vertices, as you see in the outer loop, going over all the vertices, maybe the vertices themselves are in nearby positions in memory. But when it comes to visiting the successors or the neighbors, these successors might be in very sparse areas of the memory. So this entails irregular memory accesses or random memory accesses, meaning that you might be bringing one entire cache line to the core and only use a couple of bytes or 4 bytes or 8 bytes of the entire cache line because all other neighbors are in completely different cache lines, right? So this is a problem in terms of data movement, but also an additional problem is that we are not going to make use of that cache line for a long time because there is not really so much computation to do. If you think about this algorithm, for example, this 3 lines of code correspond to the PageRank algorithm, where we just need a multiplication and an addition to update the rank of each of the successor of one vertex, right? So there are random or irregular memory accesses, very little computation. So the data movement problem or the data movement bottleneck gets exacerbated here. So potential solution, the Tesseract system for graph processing is a coarse grain accelerator based on processing in memory technologies. As you see, this is how the system, the entire system looks. Each of these is a stack of 3D memory, 3D DRAM memory, and in each of the stacks there is a logic layer containing multiple processors, multiple small processors in order cores that are communicate to each other through this crossbar network, and they can access data in the different DRAM layers in the stack. We take a closer look at each of the cores. We see that there is an in-order core that has access to DRAM through this DRAM controller, or can access the DRAM of other cores, or even DRAM in other cubes of the accelerators through this network interface. And there are some more units to perform communication across cores and also to prefetch data. So here, the one interesting thing in this approach or in this course is that you can either bring the data from remote places. For example, this core here might need data that is directly accessible to this core here, and that's something that you could do by using prefetchers, for example, or the other possibility is to use this message queue to communicate actual computation, to communicate instructions from one core to another core. So that's, those are the key ideas of the Tesseract system. Remote execution of instructions are called the remote function calls. So we are going to see some example quickly. Well, actually, based on the PageRank algorithm again. This is what I was saying. You remember, in the PageRank algorithm, we are visiting the successors of each of the vertices in the graph. Some of these successors might be in the same vault, might be in the same part of the memory, or they might be in a different part of the memory, right? So if we need to perform that update operation that consists of one multiplication and one addition, one thing that we could do is replacing that multiplication and addition that you see here, replacing it with this put remote function call. What this is doing is that is sending a request from one vault or from one core to another core to perform the update operation. That's why it's called remote function call. The good thing is that this remote function call, or the execution of this function, can be done asynchronously. As soon as one core finds, that one neighbor is in a remote vault, will send the put instruction to the remote vault, but observe that there are no dependencies, right? We can go to the next successor and then to the next successor and then to the next node or vertex of the graph, and there is no dependence across iterations, right? We send the update to the remote vault that will get updated there at some point, but we don't have to wait until that update operation is being performed. So that's why they are called non-blocking, because we don't have to wait until the computation is completely done, right? If we need that to happen, we can use a barrier, and that's something that the programming model of in Tesseract is also proposing, the use of barriers. And this is with a little bit more detail how these remote function calls are done. You have a local core. Through the network interface, you send the function and also with necessary data to the remote core that has access, direct access to the memory on top of it, and will perform the update operation, right? So, and yeah, that's why we also need these message queues, because the one core will be receiving requests or might be receiving requests from many other cores, right? And you need a queue to temporarily store those requests. Okay, what else? Well, also the prefetching capability, right? So Tesseract is very complete in that sense. You can either send computation to a remote place, to a remote core to perform the put operation there, or you can bring data from the remote from a remote vault to the local core to perform computation. Okay. So then, yeah, let's take a look at some evaluation results. And the authors of the Tesseract paper, they tried different systems or compared the Tesseract accelerator, which is here on the right-hand side, to some different baselines. The first baseline is this could be like a normal multi-core CPU. As you see, 8, well, in total 32 out-of-order cores running at 4 gigahertz, so really powerful, beefy out-of-order cores. And they have access to a bunch of memory, but this memory is DDR3. So DDR is relatively low bandwidth. So that's why the nominal bandwidth of this system is 102 gigabytes per second. It's not ideal because DDR3 is not fast memory. So what they propose as well as a second baseline is replacing DDR3 with HMC memory. It's high bandwidth memory because it's more sophisticated memory technology. In this case, the total bandwidth can be 600 gigabytes per second. But yeah, they wanted to have also another baseline as well. In this case, they replaced the out-of-order cores with in-order cores, more similar to the ones that we have here, the Tesseract cores that we have here. So in total, as you see, 512 in-order cores running at 2 gigahertz. And here we also have the same number of Tesseract cores. In total, there are 512 Tesseract cores. What's the key advantage of Tesseract? The key advantage of Tesseract is that these Tesseract cores are right under the DRAM layers, right? So they can enjoy much higher memory bandwidth. And if you account for the total aggregate bandwidth in the Tesseract core, it will be 8 terabytes per second, which is significantly higher than the external bandwidth of the HMC cubes, which is in total for these systems 640 gigabytes per second. Okay, so that's where Tesseract should have the key advantage, the fact that it has lower memory latency and much higher memory bandwidth. Okay, and that results in up to 13 times performance improvement. Notice that, well, this is normalized execution time or speed up over the first baseline, which is the out-of-order CPU system with DDR3 memory, using significantly faster memory, because remember, this goes from, it's more than 6 times more bandwidth, right? From DDR3 to HMC, more than 6 times. But due to the scaling issues of graph applications, this results in only 56% more performance, right? Or 25% more performance if you use the in-order cores. With Tesseract, and especially when we include also the prefetchers, with Tesseract, the speed up can be much, much higher. Yeah. Both types actually. That's why the fence instruction or the barrier instruction is necessary. And I mentioned, let's say, the most ideal scenario, which are the asynchronous calls that are the put operation, but the programming model also supports a get operation where you perform the update and return some value, because this value is the output result, for example, because it's necessary for further computation. So yeah, I don't remember. You can check the paper. You probably have to read this paper. You can check what are the different benchmarks that were used, but this corresponds to the evaluation of benchmarks with or workloads with different characteristics. Okay. Okay, so where is the performance benefit or performance improvement coming from? It's coming from the increased memory bandwidth, right? So if you see what's the effective bandwidth consumption, in all cases, you'll see that Tesseract provides much more bandwidth to the cores, and that's where the benefit is coming from. But it's not only bandwidth, it's also that here the authors are completely rethinking the system, because think about the graph, right? The graph is huge, so that's why you need multiple of the HMC cubes, and you're going to map the graph onto the whole memory space that you have, multiple layers in the HMC memory, right? And that also, so yeah, you need also a way of programming the cores and performing the computation, and in the end, redesigning the entire algorithm, because in some cases you're going to bring the data from abroad, or you need to send the computation there with the remote function calls that we were talking about. So there is a lot that needs to be rethought in the system, right? Not only the system itself, but how we program it and how we change the algorithm to make it more suitable for the specific hardware that we are using. And indeed, some of the benefits are coming from there. One interesting analysis that the authors did was comparing the one of the baselines, the multi-core, the baseline with multiple cores, with multiple in-order cores, using HNC memory. But they also simulated the same system that instead of using, the external bandwidth of HNC, remember that that was 640 gigabytes per second, they are simulating an HNC, ideal HNC cube that can provide in total the same bandwidth as Tesseract, the 8 terabytes per second, you see? And that improved the performance a lot, by 2.3 times, right? But still, that was really far from the performance of the actual Tesseract system that increased the speed up to 6.5 times. And so what the authors want to claim with this analysis is that a lot of the benefit of the performance improvement is coming from the programming model itself. It's coming from the way they redesigned the algorithm and made use of the programming interface that is provided by Tesseract system. Okay, yeah, in terms of energy, also a strong reduction in energy consumption, like 8 times, also pretty interesting results. And then, yeah, to start summarizing, Tesseract has advantages and disadvantages. An advantage is as a specialized graph processing accelerator. It can provide large performance and energy benefits. It's taking advantage of 3D stacking for an important workload, and it can be more general than just graph processing, even though the authors focus on graph processing algorithms, but this kind of system would be potentially useful for other applications as well. Even more modern applications than the ones that were used by the authors of this work in 2015. Today, for example, graph neural networks could probably be a pretty good fit for this kind of accelerator. But this also has disadvantages. One of the key disadvantages is that you need a lot of changes in the system. You need a new programming model, and that's always challenging because users, programmers need to learn how to use this system. Tesseract cores are specialized for graph processing. So if you want this to be, let's say, more suitable, more general purpose, you might need a different design for the Tesseract core. Cost is also a disadvantage. You can expect that HBM memory, or sorry, 3D stack memory like HNC or HBM is more expensive than DDR memory, right? So that is also going to make this accelerator expensive. And in the end, there might be still some scalability problems because we need to partition the graphs and yeah, it's go to a remote core. If you need to bring data from a remote core in the same cube or even from a different cube, not in all cases scalability is great, because you might need to have many accesses, many remote accesses. And in the end, remote accesses are at lower bandwidth than local accesses, and that may also affect the performance. And that's why some of the later works that have built upon this Tesseract system, one of the key things that they are targeting is mapping, or graph partitioning, is how you need to map the graph onto the Tesseract system with multiple cubes in order to minimize the data movement even further, in order to minimize the amount of remote accesses that you have. So it still is not a perfect solution. But anyway, the paper is there. There are also some slides that you can check. And we continue talking about near memory processing. Do you guys have any questions? No? Okay, so then maybe it's a good time to make a break now, like 15 minutes. Is that okay? Because now it's 2:30, so we will continue in 15 minutes. Does it make sense? Okay. Let me know in the meantime if you have any questions or anything that you want me to clarify. Okay, I think we can continue. Okay, yeah, remember, we are talking about processing near memory, and we are mostly focusing on processing near memory with 3D stack memories like HMC or like HVM, and we are covering different examples of how we can build processing in memory systems using this 3D stack memory technology, right? The first one is a proposal of a quartz grain accelerator for a specific type of applications in principle that have very challenging requirements, very large data sets. They also have frequent random memory accesses, very little computation. So these characteristics make the workload very suitable for processing in memory. But we are not going to design accelerators or large quartz grain accelerator for any application that might get benefit from processing in memory, right? Because that would be really really costly, and probably we cannot have so many quartz grain accelerators in our system. So there are other approaches to processing in memory. One simpler thing that we can do is extending the main memory with some compute capabilities that can perform certain operations that are important for the specific applications that we want to focus on. And that might be very much related as well with the type of system that we want to focus on, or we are focusing on. For example, in a mobile system or in a relatively small environment and embedded systems, etc., we may not need to have, for sure, not a quartz grain accelerator, but we may not need to have a strong variety or large variety of different operations to perform in memory, because these systems are potentially more specialized on different specific applications, right? So it could be nice to identify for these specific applications that are important in this, let's say, embedded or mobile environment, identifying these specific applications, what functions, what calculations can get benefit from execution closer to the memory. And that's what was proposed in this Google Workloads for Consumer Devices paper that was presented in 2018. Is a paper that we have already mentioned, because the famous 62.7% of data movement spend or energy spend of data movement is coming from this paper. And energy is in the end the main motivation for this work. Why is that? Because this work focuses on consumer devices, for example, tablets or cell phones or smartwatch, that are mobile devices. They rely on batteries. There is no connection to the electric network that can provide a continuous supply of energy, right? These systems rely on the use of batteries, and batteries have a certain duration, right? And we want to maximize this, the duration of these batteries. How? Accelerating the workloads, making their execution more energy efficient. And that's why the work focuses on these type of workloads that are typically used in consumer devices. For example, Google Chrome or TensorFlow Mobile, or the VP9 video playback and video capture applications, right? The interesting thing of this work is that, first of all, a lot of characterization work was done for these important, useful applications that are basically everywhere, right? Because they are from Google, so they are in many mobile devices that we are using these days. And one as I said, one first interesting thing of this work is that there is a lot of analysis of what's the cost of the energy cost and the performance cost of executing these applications in existing consumer devices, right? So there are some important observations for a start. The 62.7% of total system energy and spend of data movement that you already know. Some other important observation is that a significant fraction of this data movement is coming from relatively simple functions. So that inspires the authors of this work to propose logic near the memory to accelerate those simple functions in memory. But there might be different ways of doing it. You could have a more general purpose core that can execute the different operations, or you could have an array of specialized accelerators near the memory for each of the specific functions. And the authors evaluated both and saw what were the potential energy and performance improvements. As you see, more than 55 and 54% savings these are average results. Of course, we are going to see more detailed results soon for these different workloads. We start focusing on TensorFlow Mobile. TensorFlow Mobile is used in the consumer device for neural network inference. So for whatever neural network is being used, will feed some input and will get some prediction, some inference output. One first outcome of the workload characterization analysis that was done in this work is that 57.3 of the inference energy is spent on data movement, and 54.4% of the data movement energy is coming from two main functions, simple functions like packing and unpacking, and quantization that are used in TensorFlow Mobile. So we are going to see what's going on with these functions indeed, and why they are, so much. They have these large data movement requirements, and we are going to see what are possible solutions for that. If you think about packing, is a quite simple operation that just requires reordering the values, the data of matrices in order to perform matrix multiplication faster, minimizing cache misses. But doing that requires us first to spend 40% of the inference energy and 31% of the inference execution time on this packing operation, which is just moving data, right? It's just rearranging data in order to make the data structure more suitable for the later computation. And one other observation is that packing's data movement accounts for up to 35.3% of the inference energy. So lots of performance and energy are wasted due to this packing operation, even though it's a relatively simple data reorganization process that doesn't require a lot of computation, just requires simple arithmetic. The other one is quantization. In quantization, what we are doing is converting floating-point numbers into 8-bit integers. Remember that I talked about quantization earlier today when we were introducing the Samsung HBM architecture. Neural networks do not require full precision to perform well, especially in inference. So that's why quantization is a really good approach to reduce the amount of memory space that we need and also accelerate the execution, right? But doing this quantization is costly, and it's costly in terms of execution time and energy. Here you have some numbers coming out from the workload characterization analysis. A lot of the quantization energy is coming from data movement, and quantization is pretty simple as well. It's a data conversion that just requires shift, addition, and multiplication operations. So not very costly operations. What this work proposes? First of all, move the computation regarding packing and unpacking or quantization near the memory, have there either some general purpose core or some specialized accelerator. Both cases were studied and obtain some performance and energy improvements. Indeed, you can see here normalized energy. This is for the different applications that are being used in this work and different steps in these applications. We are focusing now on TensorFlow Mobile for packing, and for quantization, we see a strong reduction, more than 50%, or around, actually more than 50% in some cases, around 50% in other cases, energy savings from the execution on the CPU core, the execution on a PIM core, or the execution on a PIM accelerator. So there are very good chances of improving the performance and energy consumption of the system if we do acceleration, processing in memory acceleration for TensorFlow Mobile or for the other applications as well. And these are results for normalized runtime where we see, performance improvements as well in the same ballpark, around 50% performance improvement, just by offloading those functions that are really memory bound, as the word look characterization step has shown, right? Yeah, in the paper you can see, you can find the analysis for all these different applications. In this slide, we also have a few details about the Chrome browser. How the way that Chrome renders a web page has different stages. First of all, loading and parsing, then this layouting step where some calculations of visual elements and positions of the objects is being done, and finally the painting step. First, rasterization that paints the objects, and finally this compositing that assembles all the layers into a final screen image, right? And well, each of these steps have different requirements. The thing is that for a satisfactory user experience, what they, you as the users of the browsers expect to have is fast loading of the web pages, smooth scrolling, and quick switching if you are changing tabs, right? But yeah, these operations might be costly. That's why the focus here is on two of these operations, page scrolling and tab switching, because both include page loading entire pages, web pages from the main memory to the display so that they can be used by the user. For example, in tab switching, something that was observed is that when you have a Chrome with multiple tabs open, there is a lot of data movement that is coming from context switching and loading new pages. You have your Chrome browser and you have multiple tabs there, and every time that you switch one tab, you need to context switch, or the browser needs to context switch and load a new page, because the pages are not active all the time. If you are not using it, it's just compressed and sent to memory. And that's and that compression indeed requires a lot of data movement. What the Chrome browser does is when one tab is inactive, it's compressed and sent to DRAM. It's stored in part of the DRAM that is called the ZRAM. And whenever the user wants to open that tab again, the CPU will have to access the compressed tab, decompress, and then show the tab, show the web page to the user. All these compression and decompression operations require a lot of data movement, and this was studied with some interesting experiment emulating how a user switches through 50 tabs and how much data movement was needed. The observations are that 18.1% of the total system energy is spent on compression and decompression, and a lot of data was moved between the CPU and the ZRAM, almost 20 gigabytes of data for these 50 tabs. So how can we use processing in memory to mitigate this cost? Instead of doing the CPU-only approach, where compression and decompression are done on the host, and this requires a lot of data movement, what can be done is moving the compression operation to processing in memory, and this way save a lot of data movement and potentially use the CPU for other tasks, in the end accelerating the overall performance of the system, right? So this was also studied and tested PIM cores and PIM accelerators, and indeed I think the results are in the previous plots that we have seen. And yeah, so this is for tab switching, and that's basically what we have about this work. As you have seen, we have shown two of the examples. One is TensorFlow Mobile, the other one is Chrome browser, and how some specific operations here can be accelerated, and the overall performance of the system and energy consumption greatly improved. Okay, questions about this work or the previous works? Okay, yeah, we have a few more. Indeed, I want to cover, we have enough time, I think. I want to cover at least two more proposals. The second, the last one is kind of similar to this one because it's also focusing on a specific parts of specific applications, and one more is about the minimal offloading to processing in memory, right? What if we just want to offload single instructions to the processing in memory side, and what are the challenges that we need to face there and solutions that we need to use. But there are many more slides in the presentation showing other interesting works on processing in memory that are not only for CPUs. This is also a processing in memory solution or processing in memory proposal for GPUs, right? In GPUs as well, GPUs also suffer from the data movement bottleneck, even though GPUs these days use high bandwidth memories in a similar configuration as the one you see on the slide. But still all computation is being done on the main GPU, which is pretty beefy chip with many cores and many threads that can run concurrently on the GPU, but still all of them need to go through relatively narrow funnels to access data from the HBM memory stacks, right? Well, there are several interesting works on how to do processing in memory for GPUs. One of them is this transparent offloading and mapping presented in 2016 that identifies specific sections of the GPU kernels that are more suitable for processing in memory and offloads them to some processing elements, small GPU cores placed under the bolts of the HMC memory. And it's not the only one. This is also another interesting one, scheduling techniques for GPU architectures. This one considers different offloading granularity. Instead of relatively small sections of the kernel execution, it offloads entire kernels. It characterizes the kernels first and sees that the authors saw that there are some kernels that are more memory bound, others that are less memory bound, and depending on that, they decide where to schedule. But there are a few more works. I think tomorrow we will talk with a little bit of detail about this one because it has some interesting ideas about how to handle virtual memory management in processing in memory systems. This is an accelerator for pointer chasing applications. We are talking about different types of processing in memory, processing near memory, processing using memory, but also different memory technologies and also different places where we can have the processing near memory elements, right? We are mainly focusing on main memory and 3D stack memory technologies, but processing memory can also be done in the memory controller. For example, this work proposes a way of accelerating cache misses by an enhanced memory controller that can do sort of processing in memory, or this other one called continuous run ahead that kind of places a run ahead execution engine in the memory controller as well. So these are all interesting readings and examples of the different places where we can have the processing in memory or near data processing capabilities. Or this one, for example, we have already mentioned this one in the past, is an FPGA-based near memory accelerator, or this other one that, it's also near memory. In this case, we used HBM memory, and it's also a nice example of algorithm hardware co-design with an algorithm for approximate stream matching that is perfectly tailored to the underlying hardware. Or this other one for time series analysis. So we keep covering examples of processing in memory research works, and we have already seen how to design a coarse grain accelerator for a specific class of applications, or how to design processing in memory architectures for relatively simple function of loading. But one other question that we can ask ourselves is, what's the minimal processing in memory support that we can provide and we can get benefit from? And something that makes the integration into the end-to-end system simpler, because just minimal changes would be needed. That's the next proposal that we are going to cover. It's called PIM-enabled instructions. And instead of designing here an entire accelerator for relatively large kernels and computation, or something that implements an entire function like packing or tab switching, or the examples that we saw in the Google Consumer Workloads paper, this one just proposes to offload specific instructions, for example, an addition, or for example, dot product operation, something like pretty simple to the memory side, and still obtain significant performance and energy benefits. So the idea is to develop mechanisms to get the most out of linear data processing with minimal cost, minimal changes to the system, and no changes to the programming model. So the key idea number one is to expose each PIM operation as a cache coherent, virtually addressed host processor instruction that is called PIM-enabled instruction, or PEI, that operates only on a single block. Why is that important? Because if you think about how memory is mapped, so how data is mapped onto memory, you'll see that you are going to typically map consecutive cache lines to consecutive banks or memory channels, etc. Right? So if you need to, if you in your computation, you need to access more than one cache line, you will likely need to access more than one memory bank, right? And that requires that the processing in memory unit has access to everywhere in some way. And this access to different parts of the memory might be at with different latencies, right? Ideally, we want to access the closest memory, the local memory. Remember in HMC, for example, we have the memory divided into multiple vaults, and under each of the vaults, we can have one in-order core. For example, in Tesseract, this in-order core will prefer to access data in its own vault because that's going to be faster, right? But that's not always the case. Indeed, that's why in Tesseract, we do remote function calls, or we do prefetching to bring data from other vaults, right? But if we just perform computation on a single cache line, the biggest advantage here is that we will offload the instruction to a specific processing element near the memory, and this processing element just needs to access one cache line in its own local memory, in its own vault, if you think about an HNC memory. So that's the key idea. And because they are just simple instructions, we will just need to replace some lines of code in our program with the specific PEI instructions that we want to do. For example, if we just want to do one addition, let's just replace the addition with this PIM add instruction, okay? So advantages, we can easily modify our programs. We don't need big changes in the programming model. There are no changes to the virtual memory system. Why is that? Because the instruction starts, the PEI instruction starts its execution in the CPU pipeline, right? And the CPU pipeline itself can find what's the memory address that we want to modify or we want to update, for example, with this PIM add operation. So the CPU itself, which has a memory management unit, right, can perform the memory address translation and send the PIM add instruction to the specific processing unit that resides close to the cache line that we want to update. Remember that here we are just updating one memory address, the content of one memory address. So no changes to the virtual memory system, minimal changes to the cache coherence. Why is that? just because we are just operating on a single cache line. And as you will see, if this cache line is already in the cache hierarchy, we won't go to memory, which is something that also makes a lot of sense in processing in memory, right? Compute where it makes sense, or compute where the data resides. So we need just minimal changes to the cache coherence, and there is no need to worry about data mapping, because each processing element will execute PI instructions on data that resides closer to it in the local memory, right? In a single memory module. Okay, the key idea number 2 is related to the cache coherence as well, is that we can dynamically decide where to execute the PI. If we know that the cache line is in the main memory, okay, great, send the execution of this PIM add to the main memory and execute it there in the whatever PIM processing element that you have there. But if the cache line is already in the cache hierarchy, why do you need to go to memory? Just execute the operation in the host. Okay, and well, just for a little bit of motivation, remember the algorithm is the same we used for an example just before, the PageRank algorithm. Remember that this only needed one multiplication and one addition. The multiplication now is done earlier, but in the end, the computation is exactly the same. If you want to execute this on a conventional architecture, and remember that we will typically have frequent random memory accesses there. So we are going to bring entire cache lines to the host processor, perform some update operation, and then we need to return that cache line, probably mostly unused, right? Because of the random memory accesses. And we are moving in and out 64 bytes. That's not a great idea. We are moving a lot of data for maybe just 8 bytes or 4 bytes that we want to update. If we replace the update operation with this PIM add, we could just send the value to the main memory and perform the update operation, the PIM add operation in the main memory. And this would require just 8 bytes in. Okay, well, but executing always in memory is not always a good idea. And actually, the paper has this nice analysis for different graphs and of different size, right? So more to the right means more vertices, so larger graphs. And what the authors observe is that not in all cases offloading the computation that we have just seen in the previous slide to the main memory not always is a great solution. Why is that? Because sometimes the graphs are pretty small and they fit in the caches, or large parts of them fit in the caches. So it makes no sense to offload to memory. So there is where it makes sense to come up with ways of doing, a smart scheduling based on where the data really resides. One advantage of the PIM-enabled instructions as well is that they can be executed asynchronously. In many cases, it's similar to the remote function calls in Tesseract, right? We offload the computation to memory and we can continue doing computation if there are no dependencies, as it's this case. If we eventually need to synchronize, we can use this pfence that has a similar purpose as the barrier in Tesseract, right? So it's making sure that making sure that there are memory consistency guarantees, right? We are sure that all updates were done before this pfence. The paper, the idea itself is not limited to any specific instructions, right? PIM-enabled instructions. You could come up with your own PIM-enabled instructions. The authors proposed a few ones that were nicely implemented for the specific applications that they were targeting. And well, yeah, they have some characteristics that we have already discussed, like cache coherent, virtually addressed. They target a single cache block. They are atomic between different PIs. So if let's say you have two CPU threads and both of them are sending a PI to the main memory to execute, execution is going to be in an atomic manner. That means that if they want to update the same cache line, the execution of one update will be first, and then the second update from the second thread will come later. So they are atomicity is guaranteed, and at some point we might want to use P fences. And here you see, well, that those are more characteristics of the PIM-enabled instructions in terms of localization, interoperability, and simplified locality monitoring. So localization, key idea is that because we are targeting a single cache line, we don't need to perform remote accesses. So that's pretty convenient. It's also pretty convenient for the system integration support. Okay, and here you see some information about the different data intensive workloads that were used for the experimental part of this work. Graph processing, data analytics, machine learning, and data mining. And here you have the what are the different applications: average teenage follower, BFS, PageRank. So as you see, several graph processing algorithms, but also data analytics and machine learning. And the paper shows pretty good results. They evaluated 3 different data sets for each of the applications of data sets of different size, because if they are very small, they will likely fit in the cache memory. So PIM might make no sense. The more interesting analysis for sure is for the larger inputs, because that's where we can see most benefits from either PIM or either the locality aware execution. The locality aware execution adds a certain unit near the caches of the host CPU and locality monitor that is going to check whenever we want to update or we want to operate on a cache line with a PIM-enabled instruction. The first thing to do will be for the locality monitor to check if that cache line is in the cache hierarchy. If it's not, then we offload the computation to the memory. And that's why you see a little bit higher performance improvement for the locality aware execution, because not in all cases makes sense to offload the computation to the memory. In fact, here you see the results for small data sets where, because data sets are pretty small, they likely fit in the caches, so it makes no sense to offload all the time to processing in memory. That can only cause a performance reduction. Yeah, you see here some more results and analysis to justify the performance that we see in the other plot. These are the off-chip memory transfers. For PIM only, we are always offloading the operation to the memory, even though the cache lines might be in the host. So that requires a lot of data movement. So it's always good to understand the workloads, understand the data sets, and understand the systems in order to make the right scheduling decisions. And these are results for medium data sets that you can check yourselves. And these are energy consumption analysis. As expected, larger energy savings are for the large data sets, up to 25% energy savings just by offloading some individual instructions, these PEI instructions that can be performed near the memory. So advantages and disadvantages. One advantage of these PEI is that they are simple, and there's a simple and low-cost approach to processing in memory. There are no changes to the programming model or the virtual memory. It's possible to decide dynamically. The locality monitor does that, where to execute an instruction. But there are also some disadvantages. We don't take full advantage of the PIM potential because we are just offloading individual instructions due to this single cache block restriction. And yeah, in the end, if you have PEI units near the memory in your system, you might be able to only execute some relatively limited operations near the memory. If you think about this PEI proposal and the real-world processing in memory systems that I presented in the beginning, you'll see that there are certain similarities, right? Here in PEI, the main idea is to offload just individual instructions, simple instructions to the memory that operate on a single cache block. If you think about Samsung HBM PIM or SK Hynix AIM, they are they are implementing processing elements that are SIMD, but these SIMD processing elements are operating only on chunks of 256 bits. That's not exactly the size of a cache line as considered in this PI work, but is a relatively limited amount of data that can reside close to the processing element, right? So in that sense, it's also kind of a fine-grained type of offloading. One difference is that here in PI, each individual instruction is offloaded from the host, if the locality monitor decides that, from the host to the main memory, while in a system or in an architecture like Samsung HBM PIM or SK Hynix AIM, we could be offloading a little longer, right? A few more instructions to perform multiplication and additions on a little bit larger amount of data to perform, for example, a dot product operation. So it's not exactly the same, but there are some important similarities and at the same time, similar challenges for system integration as well. Okay, so this is the paper. Pretty likely another reading that you will do in this course. I think it's very inspiring and also pioneering work in the recent research in processing in memory. Okay, any questions? Yes.
Is there a limitation why we should use one?
I mean, it depends on the type of PIM, right? If you think about Tesseract, for example, in Tesseract, for each core is possible to access data in its own vault or in remote vaults, even in remote queues, because there is an interconnection network and the architecture itself has mechanisms to allow this remote communication, right? Either in the form of offloading computation or bringing data from outside. The idea in this work, PIM-enabled instructions, is to provide a way of doing PIM that requires minimal modifications to the system, right? Because that's important for adoption and for end-to-end system integration. So that's why the authors propose to operate on a single cache line, because for many workloads that might be fine, right? If you think about PageRank, every update just updates one neighbor vertex, right? So it's just 8 bytes or something like that you want to update. Or if you think about a histogram calculation, in histogram calculation, you have a large input image, but you can partition this large input image over the different cores that you have in the system, and each of them just needs to update one particular element of the output histogram. So there is not much there are not many requirements in terms of accessing data for the specific operations that we are offloading here. If you restrict the operation to a single cache line, first of all, that means that you can send the computation to the processing element that is closer to that cache line. So we avoid remote accesses that are always more costly because you need an interconnection network and because they need more time, longer latency, right? So that's the first advantage. And one important advantage as well is virtual memory support. Why? Because if you send the computation to the processing core and the processing in memory core, and the processing in memory core needs to access multiple cache lines in different parts of the memory, it needs to do virtual memory addressing, virtual memory address translation, right? And in order to really figure out where in the physical memory the data resides, right? So that needs more complexity in the processing in memory core. And probably you want to, it's challenging already to integrate cores inside the memory. So even more challenging if you need to have these sophisticated mechanisms such as virtual memory address translation. And you probably prefer to spend that area into placing more ALUs, which in the end are what you need there, right, to compute. So the good thing is when targeting a single cache line, virtual memory address translation can be done by the host. The host figures out what's the physical address and just sends the instruction to that core that is next to that physical address, and that's it. So it simplifies a lot the design in the system. Okay, so those are that's a key reason. Of course, it's also more limited, and if you see what are the performance improvements and the energy savings of this PI work, they are significantly lower than Tesseract, for example, but the other one is more challenging to integrate, right, and to adopt. Okay, yeah, we continue talking about processing in memory proposals, but this one is again, we could again consider it like function of loading, right? This one is also about Google workloads, but in the end, in this case, neural network models for edge devices, similar motivation again, edge devices will likely rely on batteries, right? And we are very much interested in accelerating their performance and minimizing their energy consumption. And this is called the MENSA framework. And the MENSA framework, well, proposes different accelerators for the different layers that we can find in ML models. Again, well, there are, if you think about mobile device, potentially with an edge TPU, it might need to make use of different ML models. Back then, when this work was done, these models were recurrent neural networks or convolutional neural networks or LSTMs or recurrent convolutional neural networks. That is different types of neural network models that have some similarities, but they also have significant differences. And that's, again, understand your workloads before you accelerate them, before you figure out how to improve their performance of the system. You need to understand them well. And that's, again, why some interesting workload characterization work was done in this project. Here, this graph shows the float over byte versus the parameter footprint for different neural networks and different layers of these neural networks. These flops per byte represent the arithmetic intensity. So when we say bytes, it means the bytes that we are bringing from the memory to the processor or to the accelerator, in this case, the edge TPU, and the flops are the number of floating point operations that we perform per byte, right? Per each of the bytes or data that we brought from memory, right? And as you see, this arithmetic intensity changes a lot from some models to other models, or from some layers of the models to other layers of the models. And at the same time, the parameter footprint, so what's the size of the layers themselves, the weights of those layers might also change a lot. And as you see, well, several orders of magnitude difference depending on the type of network and the type of layer. We can even do more analysis, because even within the same layer, we may have, or within the same network, we have layers with very different characteristics. For example, in one of the CNNs that was analyzed, there are large differences in the number of multiply and accumulate operations that are performed in different layers, or the arithmetic intensity, again, flops over bytes. It's very different in different layers. So what could be ideal? Does it make sense to have a single type of processor or a single type of accelerator for all these different models and all these different layers? The answer is no, right? Because if you have just a monolithic accelerator, such as the baseline edge TPU, which might be a nice design with a systolic array to perform, you know, a lot of the computation in all these networks is dot product, GMV operations that map pretty well onto this systolic array. But as we have seen, size of the parameters, number of operations that we perform per byte changes a lot in different models and in different layers. So that's what makes the monolithic accelerator inefficient in many cases. So the idea in the Mensa framework is to characterize the models, and depending on the characteristics of the models, define different families of workloads, meaning neural network layers or neural layers of the different neural network models, classify them, and based on their characteristics, offload them to a different type of accelerator. The first of the accelerators is pretty similar to the original baseline monolithic accelerator and is near the CPU. Why is that? Because this one is going to accelerate workloads with higher arithmetic intensity, workloads that can take advantage of the large cache hierarchy in the CPU. So when you bring data from the memory to the CPU or to these caches here, you can reuse that data several times, right? And that amortizes the cost of bringing the data and makes an efficient use of the hardware that we have here. But that's not the case in all cases. We have a strong arithmetic intensity variability in the different families. So that's why it might make more sense to design other accelerators, two more types of accelerators that sit near the memory in the logic layer of 3D stack DRAM. And yeah, the paper itself, I don't know if you will have to read this one or not, but it has really interesting analysis of the different layers, how to identify the different families, and depending on what's their memory footprint or arithmetic intensity or number of or MAC intensity, number of multiply and accumulate operations. Some of the layers will be more compute bound or compute centric, or more data centric or memory bound, and depending on that, observe that here 5 different families were identified. So families 1 and 2 are more compute centric, so they will likely be executed on the accelerator 1, while the others are more suitable for the near memory accelerators. And the overall energy reduction of Mensa for well, baseline, or either baseline with high bandwidth memory, or the Mensa framework itself with the 3 different accelerators, as you see, the energy consumption reduces by 3 times compared to the baseline edge TPU. It's a pretty nice breakdown of the energy consumption with you know, each of the parts of the bars corresponds to the energy consumption in each of the individual components of the system. So pretty nice analysis for the different models that were evaluated, and the average is there on the right-hand side. And this is the throughput improvement, 3.1 times higher throughput, inference throughput than the baseline. Also for, yeah, the plot here is normalized to the baseline with HBM memory and the Mensa framework, pretty significant performance improvements. Okay, well, you can find much more in the paper itself. And yeah, I guess we can continue. Do you guys have any questions about the Mensa framework? Okay, let's keep making progress. I think we are going to have time to start introducing the UpMem architecture and the and how to program the UpMem system. I think that's good, because that will give us more time for tomorrow's lectures, to go deeper into tomorrow's lectures. Okay, so this is the Mensa paper, but yeah, this is another one that I mentioned before. This Tom paper, transparent offloading and mapping. It's as you'll see, is a pretty nice proposal to identify what code can be executed near the memory and what are the best ways of mapping data to take advantage of processing in memory system, of loading the code, when to make use of the pin system is always a question in all types of proposals, and something that is usually targeted in the different papers. But there are more questions that need to be answered. We are going to talk about them tomorrow with more detail. But yeah, here in these slides, we already have some sort of introduction to these issues. For example, how to keep it simple, right? Remember what's the main motivation for this team-enabled instructions work. Keeping the modifications of the system small, keeping them simple, but still be able to enjoy or take advantage of processing in memory capabilities. And there are more questions to answer, right? One of the advantages of the PI work, the previous slide, is that it's a single cache line, so it's much easier to handle virtual memory address translation, handle memory coherence, but in some cases, especially for example, in this lazy pin work, when you have both the PIM units and the CPU or the host processor accessing memory at the same time and potentially working concurrently on the same data sets, you need to enable cache coherent mechanisms between the memory side and the CPU side. Why is that? Because the one PIM core might be updating the content of one specific memory address, and maybe the corresponding cache line is already in the cache hierarchy, right? And the CPU could be reading stale data if the processing in memory core updates the contents of that cache line that is already in the cache hierarchy. So we want to keep data coherent across the entire system, and that's what this lazy pin work tries to do. I think we are going to talk about this one tomorrow, but yeah, here you can see that, yeah, that's indeed possible. The lazy pin approach got pretty close to an ideal pin system with no coherence overhead. Yeah, I think we will elaborate more on this tomorrow, and this is a follow-up work that is called Conda that yeah, also proposes efficient cache coherence support. And in the pin system, we typically have multiple cores, right? That's the kind of a scenario that we are considering in all cases, right? In Tesseract, for example, is a coarse grain accelerator with many Tesseract cores that need to communicate, and the work itself proposes ways of performing this communication or synchronization. Remember that there are barriers, right? What the barrier guarantees is that the execution of all PIM cores stops when the cores reach that barrier until all other cores, all other threads in the system have reached the barrier. And right after that, execution resumes, right? So there are ways of synchronizing across PIM cores. Some of them might not be efficient in all cases. If you have 1,000 cores in a system and you want to synchronize the 1,000 cores in the system, it will probably take a few cycles to perform the barrier operation. That's why this more recent work from 2021 proposes efficient ways of performing synchronization in a processing in memory system with many PIM cores. I think we will cover this one as well with some detail tomorrow. And so yeah, support for virtual memory. We are already discussing ways of supporting virtual memory. In PI, we have seen one example, but we might need more complex ways of supporting virtual memory. And in tomorrow's lecture, we will talk about this work presented in 2016 that has a pretty nice way of supporting virtual memory in the processing in memory course. Okay. Yeah. So those are some of the, let's say, barriers that we still need to overcome in order to support processing in memory in real systems, right? How to enable processing in memory in the real world. That's a question that has many different phases, and for each of these phases, we need different solutions, right? And one other thing that we need to enable processing in memory are real systems that allow us to experiment with processing in memory and explore what are the potentials of processing in memory for different workloads. That's why we can consider this part, processing in memory in the real world, as part of eliminating the adoption barriers. In this course, you already know you are going to have a lab where you will need to program a real world processing in memory system from AppMem. You know, the most interesting thing of that experience is that you don't, I mean, for you, it's going to be, I think, pretty nice because it's a parallel programming lab. So you can refresh a little bit on parallel programming, which is good. But at the same time, you will see as well what are the issues with using a real processing in memory system, right? What are what's the potential that you can have for performance improvement, but also what are the limitations that the system has. So working with a real system allows us to understand what's the true potential of this real system, and identify its inefficiencies and propose ways of improving the system and overcoming those inefficiencies, right? This way we can build more energy efficient computer architectures and high performance computing architectures with minimal data movement, okay? So yeah, so these are, you know, different points that we will cover in tomorrow's lecture in more detail, but starting from the top, applications and software for PIM. If we want to enable processing in memory in the real world, we need to understand existing processing in memory systems. We need to understand how to program them, how to make use of them, and how software needs to be written, because likely we will have to learn something else to make use of these processing in memory systems. And that's something that it's okay as long as we get improvements, we get benefits from doing that, right? 15 years ago, when GPUs became general purpose, people had to learn how to program these GPUs for general purpose processing. And that's why many people started to learn how to program in CUDA or in OpenCL. And today you will find GPU programming courses in probably all universities teaching computer science. And that's something that makes sense to do because we are using GPUs for important workloads these days, right? Of course, before, you know, GPU programming became mainstream, it was necessary to show what were the large potential benefits from using GPUs for general purpose computations. So at this time, we are more or less in a similar situation. So that's why we need to understand what are the potential benefits of processing in memory. And at the same time, we need to develop ways of making the use of these processing in memory systems easier. And that, yeah, that's basically what we are trying to do here. So that's why we want to experiment with a real world processing in memory system. We have a little bit of experience with this AppMem PIN system. We have studied it in several papers. This was the first one we published, and we have made open source a lot of code as well for this PIN system. This is a benchmark suite that we developed in the first work, exploring different compute patterns for this processing in memory system. And that, well, as you already know, is based on DDR4 DIMMs with small processors inside the DRAM chips. And this slide actually is coming from the vendor itself, from AppMem, where you can already see what are some of the promises that they make in terms of energy savings, in terms of speed up as well, like, you know, estimations about 20 times or 10 times faster than doing it on the CPU. But that probably was not for free. One thing that they are claiming here in this slide is that fabricating chips, DRAM chips with processing elements is pretty challenging. This is something that I mentioned briefly in the beginning of the lecture today. transistors are significantly slower inside DRAM because they are designed with different characteristics, right? We don't want a transistor to be so fast because they have a different purpose. They are just switches that that connect one DRAM cell to the bit line, and they have a different purpose, right? And so typically the logic in DRAM is less dense than in the ASIC process in CMOS. So there are not so many metal layers for routing. So that makes designing a processor inside the DRAM chip much more challenging. But in the end, they made it and they filed patents about that. And I like this abstract of the patent because it already tells us what the system is about. First of all, it's a memory circuit that has a memory array, as we could expect. And then inside the memory array, there is a processor. It's called first processor here. It's a small processor. In the actual product is called DPU, as you might remember. And there is also a control interface. Why do we need a control interface? Because this first processor in reality is sort of a slave of a central processor, which is the CPU or the host, right? So the central processor sends requests to the first processor, sends kernels to be executed by the first processor. And while the first processor is computing, the DRAM banks are only accessible to this first processor. And the memory banks become accessible to the central processor when the first processors are already done, right? So this is what the system is about. In the end, we should see the UpMem DIMMs, the UpMem PIM DIMMs, we should see them as an external accelerator. In that sense, if you think about the system that we are starting to describe now, you'll see that it's sort of a quartz grain accelerator in a similar way as Tesseract was, right? Even though the memory technology is completely different because this is DDR, the other one was HMC, and the type of processors as well are different, but we can see this UpMem system as an external accelerator. So it resembles Tesseract, but also resembles GPU computing, where the GPU is a, let's say, beefy accelerator that sits on the other side of the PCI Express bus. And when we want to make use of it, we'll have to send the data from the CPU memory to the GPU memory, then perform the computation on the GPU memory, and finally return the results to the CPU memory, right? So this is what we are going to do with this UpMem PIN system as well. We will have, first of all, the CPU, in this slide called SoC, system on a chip, right? The CPU loads data to be processed to the DRAM memory bank. The DRAM memory bank here is the PIM-enabled memory, right? Then transmits a data processing command to the DRAM processors, to the DPUs. It's like launching the kernel onto the DPUs, and then the execution by the DRAM processors start, right? These DRAM processors compute for certain time, for certain number of cycles, maybe millions of cycles. And in the meantime, the CPU would be checking whether the computation has finished or not. Because when the computation finishes, the banks become again accessible to the CPU that can go there and bring the data, bring the results, right? So observe that is pretty similar to what we do in the GPU computing as well. And here you have another picture of the, or of the first picture of the system organization. Is pretty simple because it's coming from the patent. You can see the CPU there, and then you can see the different DRAM DIMMs or DRAM chips with memory arrays and with processors. But here you have another, let's say, different picture of the entire system with the host CPU, the main memory, because still there are conventional DRAM DIMMs that we use as main memory, and the PIM-enabled memory, the PIM-enabled DIMMs. And we can take a closer look at each of these DIMMs. The DIMMs typically have, well, 1 or 2 ranks. The most recent ones have 2 ranks of 8 chips, right? And in that sense is pretty similar to conventional DDR4 DIMMs. And then in each of the ranks, we have 8 chips, and inside each of the chips, we have these. we have 8 DRAM banks. Each of the DRAM banks has a size of 64 megabytes, and they are called MRAM, right? Even though they are, let's say, conventional DRAM. And on the other side, what we have is a processor, a small processor. If you look at this, it looks like it's a pipeline, right? It looks kind of similar to the MIPS pipeline, for example, that you might have studied in your bachelor courses, right? I think, yeah, we will likely have more detailed slides of this, but anyway, as you see, we have 8 DRAM banks. Near each of the banks, we have one pipeline, and there are 2 small SRAM-based memories. One is for instructions, and the other one is for operands. This one behaves as a kind of cache, but is not exactly a hardware-managed cache similar to what you have in your CPU, in your laptop, or your cell phone. It's not hardware managed. This one needs to be managed by the programmer. So we should explicitly request accesses of data, or request data from the DRAM, bring the data from the DRAM to the WRAM, and then the scratchpad or software managed cache. And then once we have the data here, we can use it, we can operate on that data using the ALUs, okay? Yeah, we will see this in more detail later. This is another picture of the, let's say, current UPMN-based pin system that has up to 20 DIMMs, in total 40 ranks. So in total, 2,560 DPUs. As you see, is a dual socket CPU connected to main memory and to PIM-enabled memory. In the PIM-enabled memory, we have all these many DPUs, and in total 160 gigabytes of PIM-enabled memory. And this is one picture that you have already seen before. Probably now it makes much more sense, right? You can see all the DIMMs there in the memory slots. Some of them are devoted to the PIM-enabled memory, while others to the main DRAM. Okay, any questions so far about this system? Okay, so then let me continue, and for maybe 4 or 5 more minutes, and we will be done until tomorrow. We're going to talk again about this UPMN pin system and about how to program it. We will not cover the entire presentation about this system for sure, but I want to give you the basic background on UPMN programming, at least, because that's what you need for the lecture, for the lab. Sorry. As our first example, vector addition. This is the simplest thing that you'll have to program. It's our first programming example. In vector addition, the only thing that we are doing is the element-wise addition of 2 input vectors, A and B, and storing the output in a vector called C. What we do if we have a system with multiple processors, and the processors here are called DPUs, what we will do is partitioning the workload across the different processors. Imagine that we have 4 DPUs. Okay, so we divide input and output vectors into 4 large chunks, and we assign each of them to each of the DPUs. What should be the size of these chunks? Well, it depends on the amount of memory that you have in each DPU. You guys remember how much memory? We have access to a DRAM bank of 64 megabytes. Right? So that's the DRAM that we have for each of the DPUs. So that defines what's the largest chunk that we can assign to each DPU. But then inside the DPU, inside the, I will call it DPU, or sometimes maybe PIN core, right? So inside the DPU, we are going to have multiple threads running, right? In the same way as you can program threads with OpenMP or P threads or C++ threads in your multi-core CPU, something similar, we can program these DPUs to use multiple software threads that are called tasklets. So inside each of the DPUs, we are going to partition the workload again, and we'll assign different chunks of the input to different tasklets. This way, we can exploit the large data level parallelism that this simple vector addition has. Okay. By the way, typical numbers are not 4 and 2. Here we have more than 2,000 DPUs, as we have seen, more than 2,500 DPUs, while typical number of tasklets are more than 11. We will see why tomorrow. And typical number that you will use in your lab will be 8, 16, 12, something like that. The maximum number of tasklets in each DPU is 24. Okay, here you can see, a link to the user manual. Actually, that's an old version. There is a newer version from 2023. It's a key reference for you, not only our lectures, but you can also access the SDK documentation that explains everything, all the different things that you need to know to make use of this system and program it. I would like to first, and I will finish the lecture here, give you some general programming recommendations that come from different places. So first of all, but as you will see, they are kind of intuitive, right? They make a lot of sense. So if you want to make use of an accelerator, like the entire pin system is an accelerator, right? Remember, we can see it as a coarse grain accelerator. We probably want to accelerate the workload as much as we can, right? We have a lot of bandwidth, a lot of pin cores. So why not? Let's try to use them as much as we can. So that's why one general programming recommendation is to execute on the DPUs, on the DRAM processing units, portions of parallel code that are as long as possible. That's something that you would do in this system, but you will also do in other types of accelerators as well. Because if you offload more computation, that means that you will have less communication between the host and the accelerator, right? Between the host CPU and the pin system, or between the host CPU and the GPU, if we are talking about the GPU. So this is kind of general because it does not only apply to the pin system that we are working on here. Okay, so second important thing, or second important consideration, is to split the workload into independent data blocks which the DPUs operate on independently. Why is that? Well, first of all, because if you are a pin core and you have direct access to some part of the memory that you can access faster than other parts of the memory, well, you want to stay there, right? Because the performance will be higher if you are accessing the local memory. That's something that makes sense everywhere. It makes sense in Tesseract as well, right? As we have discussed, but it makes even more sense in this pin system. Why is that? Because each individual DPU has only direct access to its own DRAM bank. So all communication between DPUs, as we will discuss in more detail tomorrow, needs to happen through the host CPU. So that's not a good idea, and that's why we want to work on independent data blocks. Of course, if you have a parallel system and you want to accelerate the performance of your workload, you should use as many processing in memory cores as you want, as you can, right? So there are more than 2,000 or more than 2,500 DPUs in the system. Use as many as possible. And finally, launch at least 11 tasklets. Remember the software threads that run on the DPUs. Why 11? Well, I think that we are going to see this tomorrow, but it's related to the number of pipeline stages. Remember that the DPU is a in order pipeline processor, and it has a certain number of stages. So we really want to keep all stages in the pipeline busy, and that's something that we can do when we have at least 11 threads, 11 tasklets. Okay, any questions? No? Okay, so then I think it's enough for today. We will continue tomorrow with this admin programming. We just started. It's going to be a little bit longer, probably the first half of tomorrow's lecture, maybe 1 hour. So we will talk about admin programming lecture 4A, and then we will continue talking about processing in memory in the enabling PIM lecture that is 4B. So yeah, thank you very much for your attention and see you tomorrow.